4.7 is solving counting problems. So we're putting together everything that we've done in this unit with fundamental counting, principle, and permutations and combinations, and figuring out which is the ones we need to use to solve problems. So our first example here says, Mr. Rice and some of his favorite students are having a group photograph taken. There are 3 boys and 5 girls. The photographer wants the boys to sit together and the girls to sit together for one of the poses. How many ways can the students and teachers sit in a row of 9 chairs in these poses? So if we take a look at this then, what we're doing is we're arranging these people, right? So Mr. Rice is one person that's being, being arranged, so he's going to have one spot. And there's only one of him, so there's only one way to arrange him. We have the boys, and there were 3 boys. So that means there's 3 ways of arranging them. And then we have the girls. So in the girls, there were 5 of them, so we can arrange them in 5 factorial ways. Altogether, though, so besides that, we also have the fact that we could switch these around as rice boys girls, rice girls boys, boys rice girls, girls rice boys, and so on, girls boys rice. So we can arrange those in 3 factorial ways. So that means that altogether then there are 1 times 3 factorial times 5 factorial ways that we can arrange, and then times that other 3 factorial way. So the number of seating arrangements would be 4,320. And you wouldn't think it'd be that many when all you're doing is working with 9 people. But because those people can be arranged differently within their groups, you have to include all of those. Example 2. Looking at problem solving involving cases, and we did some of these. When we're looking at cases, those are the questions that say be at least, or no more than, or have to be 6, something like that. So it says a standard deck of 52 playing cards consists of 4 suits, spades, hearts, diamonds, and clubs, of 13 cards each. How many different 5-card hands can be formed? So this is a choice question. We're choosing cards. It doesn't say in here that we have to, what is the number of arrangements we can have if hearts are picked first or whatever. This is just saying how many different 5-card hands can we have. So this is order not important. So that means then we have 52 cards that we're choosing 5 from. So that's 52 factorial over 5 factorial times 52 minus 5 factorial. So when you do the math on that, and you can do your calculator, do that 52 math PRB factorial button, or the combination button, actually the C, and then 5, and press enter, and you get your total of 2,598,960 5-card hands are possible. B says, how many different 5-card hands can be formed that all consist of hearts? So we have 13 hearts that we're choosing from. So we have 39 non-hearts. So from this 5-card hand, 13 choose 5 are going to come from our hearts, and then we're going to be choosing and 0 from our 39 leftover cards. This is just the same as 1. Oops, shouldn't put the equal sign there. Because you're saying 39C0 is just saying 39 over 0 factorial times 39 factorial. So it's really just 39 factorial over 39 factorial. It's just a good idea when you're doing these to include this, so when you're doing the other questions, you remember that you have to pull your remaining cards. If this had been a 4, we'd have to choose 1 from the other 39. So this is 13 factorial over 5 factorial times 8 factorial, so that's my 13 minus 5. That's how I got that. Times it by 1 is 1,287. 5 card hands could be all hearts. How many different 5-card hands can be formed that consist of all face cards? So in a deck of cards, you have Jack, Queen, and King are your face cards in all 4 suits, so that means that there are 12 face cards. So we have 12 choose 5. Times 40 choose 0. So anytime you're choosing 0, there's only one combination of doing that. So and this should say 40 non-face. So this is the same as 12 factorial over 7 factorial times 5 factorial, 792 5-card hands that could be all face cards. How many different 5-card hands can be formed that consist of 3 hearts and 2 spades? So we're getting all 5 of our cards from our hearts. So we have 13, choose 3 for our hearts, times 13, choose 2 from our spades. And you could then include your 26, choose nothing from the other ones. So this is more of an optional. It's just a good thing to remind you that when you're doing some of these questions where you haven't used up all the cards, you have to take the remaining out of what's left. So this is 13 factorial over 3 times 10 factorial, 3 factorial times 10 factorial, times 13 factorial over 2 factorial times 11 factorial. So this equals 22,308. E says, how many different 5-card hands can be formed that consist of at least 3 hearts? So we have case 1, where we would have 3 hearts. So this is our direct way of solving it. So we would have 3 hearts, and the other 5 cards would be 2 non-hearts. So that could be clubs, diamonds, or spades. So in that case, we would have 13 choose 2 times 39, sorry, that should be choose 3 times 39 choose 2. Case 2 is if we have 4 hearts, so that means we have 1 non. So that is going to be 13 choose 4 times 39 choose 1. And then case 3 is if we have 5 hearts, 0 non-hearts. So this would be 13 choose 5, whoops, that got a little big, times 39 choose 0. So in order to find what this answer is, you add up all of these cases. And we add them because you could have 3 hearts, 2 non-hearts, or 4 hearts, 1 non, or 5 hearts, 1 or 0 non. That or means we add. And means we multiply, or means we add. So add all the cases together. And you get 241,098 different hands consists of at least 3 hearts. So your indirect way to solve this would be to figure out how many 5-card hands you have. Whoops. So you'd be doing 52 choose 5, and then you would subtract the possibility, oh no, will that work for this one? No, can't do that for this one, sorry. The other question that we did in the other chapter, or in the other section, was if it was a case where you had, what's the word I'm looking for? It was an at least one question. So then it was, since it's an at least one, you can do the indirect reasoning with it, but you can't for this one. Okay, F says, how many different 5-card hands can be formed consisting of at most one black card? So case 1, at most would be you would have 1 black and 4 red. So that would be 26 choose 1 times 26 choose 4. Case 2 would be if you had 0 black and 5 red. So that would be 26 choose 0 times 26 choose 5. So if you add up all of those cases, so do your calculate 26 choose 1 times 26 choose 4, and then do your 26 choose 5, add those two together, and you will get your answer of 454,480. So in this one, you could also do indirect reasoning because it's got the one stipulation in there. So to do this, you would need to consider the total number of 5-card hands you would have, as well as the number of 5-card hands that do not meet the condition of at most 1 black card. So that would be, total number of hands would be 52 choose 5. The number that would at most not meet that condition, oops, not times, it would be a minus, would be from your red cards. It would be if you had 26 choose 4. Now if you do those two and subtract, you should get the same value. I could be lying to you, but I think I'm right. When solving counting problems, you need to determine if order plays a role in the situation. So remember, if order matters, then you have to use permutations. And if order doesn't matter, if you're just looking the Chinese food scenario, then it doesn't matter what order you put your food on the plate, you just have to order a combination of food, then you would use the combination formula. Look for any conditions. Consider these. First is you develop your solution. If there is a repetition of R of the n objects to be eliminated is usually done by dividing by r factorial. Okay, and that's what we did in the combinations. That was one of the differences between the combinations and the permutations formula, is to get rid of repetition of the objects, we divided it out. If a problem involves multiple tasks that are connected by the word and, then the fundamental counting principle can be applied. So that's like the social insurance number situation, where you had 10 digits, and you have 10 choices for the first spot, 10 for the second, and 10 for the third, and 10 for the fourth, unless there's a restriction on there. And we multiply the number of ways each task can occur. If a problem involves multiple tasks that are connected by the word or, the fundamental counting principle does not apply. Because we're not multiplying them anymore, we are going to be adding them. So add the number of ways each task can occur, and this typically is found in counting problems that involve several cases. So that's the at most or least type questions. Okay, that's all for this section, so it's the last section. Our test will be coming up. Do these practice questions in your book, and good luck.